Today we are going to be looking at problem 11.27, which is a heat exchanger problem. We're given a counterflow twin tube heat exchanger. We are told the length of the tubes, their diameters. One of them has water going through it, the other has air. We are also given a contact conductance of the joint between the tubes, the mass flow rates and inlet temperatures of both fluids. The problem does tell us that we should use effectiveness NTU and asks us to determine the outlet temperature of the air. They also give us a little hint here at the end that tells us to treat the tubes as extended surface. And then they also give us this little picture showing the two tubes and the two fluids going in opposite directions.
Alright, so to start, I've gone ahead and just drawn a little schematic, copying the one from the problem, and then just written out the given information, flow rates and temperatures for each of the fluids, as well as that contact conductivity in that joint right there. I've also just gone ahead and written a couple of assumptions. First of all, that there is negligible heat loss to the surroundings, and also that both the water and air are in fully developed flow. So heat exchanger problems are pretty complicated, and this one included. And so I think it's important to, before you start doing any math, establish what it is that you need to calculate to get your final answer, so you don't do more than you have to. And we are looking for that outlet temperature of the air. We end up finding this equation in purple that has the air outlet temperature as a function of other temperatures and the C's, which are easy to calculate, but that effectiveness. And that is going to be the thing that is a challenge to calculate, and why we're going to have to use the NTU method. So we've established what we need to calculate. The first step in doing that is going to be calculating the overall heat transfer coefficient, and that is that big capital U. In solving for the overall heat transfer coefficient, the first step is going to be solving for the convection coefficients of both fluids. So I've shown that process for the water here. It's just internal flow. First, you're going to calculate Reynolds number. We get 11,243 here, which means it is turbulent. And that gives us this equation here for Nusselt number. Solving that, we get a Nusselt number right about 55. And then we can plug it in to this equation and calculate the H of our water, which is 3,607 watts per meter squared Kelvin. For the air, you can do the exact same process of Reynolds number, find an equation, solve for Nusselt number, and then solve for H. And then for the air, you will get 395.3 watts per meter squared Kelvin. So now that you have both of those numbers, we can go ahead and write an equation for capital U. Looking at our overall heat transfer coefficient UA here, I've written the equation out in purple again because I think it's kind of fundamental for this problem. We see the first thing weird is this middle term. This is a conduction term for that joint there. Remember, they gave us this conduction coefficient. So we just need to factor that in, 1 over KL. And then these two terms are our convection terms for the water and air. And in looking at those convection terms, we notice the H's that we've already calculated. There's also an area, which isn't that hard to find, but we have this efficiency term there. And that one is going to be a little more challenging. So I think next we're going to jump into that and see how that one's going to work. Looking at our equation for efficiency right here, we see that it uses a hyperbolic tan, and then it's just a function of m and L. The only problem with that is that neither m or L are what you expect them to be. M is not mass. It is actually this little equation here, h over kt to the 1/2, which is not too hard to calculate. And L is not this length. L is actually going to be calculated with 0.5 pi d, d being the diameter. Let's go ahead and calculate that. So doing both of those calculations, we end up with an efficiency for water of 0.435. And again, just like over here, for air, the calculations are essentially the same. So for air, we end up with an almost identical efficiency of 0.438. So there are our two efficiencies. Now we just have to really quickly calculate those areas, just the surface areas of the tubes. So equation is just pi dl, and there are those two areas. Now we have everything that we need to find that heat transfer coefficient. I think since we're running out of space, I'm going to put it right here, get rid of that stuff. Let's take that equation and plug in some of these numbers and see what we get. Plugging in these numbers and some from up here into this big equation, we're ended up with this and an overall heat transfer coefficient of 437 watts per Kelvin. All we need now to calculate NTU is the specific heat capacity that also shows up here and here, and that is capital C. Capital C is a pretty easy equation calculated from m dot and lowercase c. So let's go ahead and calculate both of those for the water and for the air. After that quick calculation, we find C water and C air. And the other important thing to know from these is that we now know that C air is our C min and CW is our C max. From knowing that C air is min and C water is max, we can calculate our C ratio, which is min over max. Gets us a CR of 0.722. That's just a ratio. Now we have everything we need to calculate NTU and then effectiveness. So I think I'll go ahead and erase this stuff and calculate NTU. NTU is just the overall heat transfer divided by C min. And we get 3.62. That is not too bad, but what is bad is this. That is the equation for effectiveness as a function of NTU, and it's not the nicest looking equation, but we do have everything we need for that. So let's go ahead and fill those things in really quickly and find our effectiveness, which is the last thing we need for our fundamental equation up there. So plugging in, we get a final effectiveness of 0.862, which is reasonable. And so now the only thing that we have left to do is to rearrange this equation to solve for that outlet temperature and then plug in and solve. So I will erase this stuff and plug those numbers in. I took the purple equation here, did a little algebra, rearranged some stuff, plug in some numbers, and then we get a final outlet temperature for the air of 76.4 degrees Celsius. So there is our final answer.